He's going to talk about the UNSW ECO. He has a PhD from UNSW in 2012. And he's been in charge of the two satellites that we've been sort of putting up. I'll tell you all about it.
Hi everyone, good morning. Today I'm going to talk about some of the updates from UNSW ECO, which is Australia's first 3 CubeSats in space. It's also our UNSW's first CubeSat that's operational in orbit. I'm Joon, and I'm the technical lead for a team of volunteers basically working on this CubeSat. So this is a visualization of the external parts of our CubeSat. We can see that there are solar panels. We have actually 5 one-use solar panels on the externals, science unit, and a couple of antennas poking out at the back. These antennas are initially to be stowed on the CubeSat and to be released by a burden resistor once it's inserted into orbit. We'll move on to sensing. So these are the components that are inside the spacecraft. These are actually off-the-shelf camera modules that can perform some attitude sensing from using the sun and the earth. And also we've got some magnetorquers to actuate ourselves. We actually wrote our own ACSER algorithms to control the magnetorquers and also to perform some filtering using some ECR to smooth the attitude sensing data from the attitude sensing boards and inertial sensors. So our structure is somewhat unique in the sense that we've actually 3D printed our structure. The structure is made out of nylon printed material that allows us to have flexibility of having hinges wherever we want it to be, having holes, and having this reinforced segments that we needed it to be to survive the launch. And the nylon, once it's fully printed, will be coated with silver, and once it's coated with silver, we electroplate it with nickel, provide a very good finishing that is highly conductive, so that we can have a very good character of thermal gradients. Moving on to comms, each board on the bus can actually talk to each other via CubeSat space protocol. That's one of the perks of using the CubeSat modules. The CubeSat space protocol sits on an I2C bus, and I2C bus itself, however, is somewhat unreliable. It's that in some of the past missions we've known that I2C bus can lock itself up and requires a reset of certain modules for I2C bus to be freed up for other modules to talk to each other. So if any of these items hangs due to a software anomaly or whatnot, it can actually pull one of the lines down, and any of other modules that are still operational that can talk to each other will not be able to talk to each other because of this one single malfunction. So to work around that, the EPS that we purchased from ComSpace actually have a watchdog to look at the I2C bus to make sure that if there is a lockup, all the modules will be power cycled to prevent that from jeopardizing the entire mission. So it would have a timeout of 10 minutes, and if there has been no I2C bus activity for more than 10 minutes, it will actually power cycle the entire bus down. On top of that, there's also other watchdogs available on this EPS to make sure that any software anomalies can be recovered from. And also there are different power modes that would allow us to actually be power conservative when necessary and allow CubeSat to still be able to reach us, and we can still reach the CubeSat to perform certain communications and telemetries. So the beginning of the story is in April 2017. We were launched on the ISS. We made a bit of the news when when we were launched, together with three other Australian Cubesats to the ISS. And once we were in the ISS, we had to wait about a month. So this is about May when we were inserted into orbit. So upon insertion into orbit, it's part of NanoRac's regulations for our CubeSat to be turned off, to be radio silent for 30 minutes. And once 30 minutes has passed, we're allowed to deploy our antennas and start beaconing. And the story was that we were not able to retrieve any beacons on its first pass over Australia and its subsequent passes either. So we tried then to uplink some commands to the CubeSats, and we also were not able to get any response back from that from our CubeSats as well. So we quickly started to brainstorm for some ideas on what might be the case. The CubeSat does have some low battery mechanisms whereby it will low battery modes whereby it will prevent the antenna deployment from happening if it does enter low battery mode. So we might have to wait for it to charge up from low battery mode such that the deployment can actually happen. It will also periodically redeploy antennas if some of if a certain flag on that bus hasn't been set. So we were waiting for one of those things to happen, but none of those did. So we started to devise a rescue plan to figure out what could be the core cause of the failure and trying to recover from it. So we found there are three dominant scenarios that could have caused this, and we've isolated one to be a particular case to discuss today, and that is the EPS I2C watchdog. So it turns out that the EPS I2C watchdog would actually reinitialize the 30-minute timer every 10 minutes. So 30 minutes timer will start counting down from 30-minute mark. Once it's reached 20 minutes, it will reset, comes back out 30 minutes. So it will consistently be within that 30 minutes deployment loop where it will never come out of. So the solution was to configure the onboard computer to disable the 30-minute deployment countdown timer, and also to force deployment of the antennas to happen, and to tweak some of the EPS settings so that communications can be optimized and the power settings can be optimized. We replicated these commands on the engineering model that we had in our lab. Those commands were able to recover from all three identified possible causes of this issue, and recorded that into WAV file so that the other radio amateurs can upload it for us. Now you would ask, well, why did this problem occur in the first place? So we did have very thorough testing that we've conducted before we actually sent the spacecraft for integration and launch. And during the test, as part of the test procedure, we had to make sure that the test was set up correctly. And part of that checks requires the OBC to be interrogated, and that interrogation actually resulted in some I2C transactions occurring on that bus. So as a result, we did not have the EPS I2C watchdog resetting the system, and we actually had many successful deployment and antenna deployment tests conducted in our labs. So this is a snapshot of the signals that were transmitted to the satellite to rescue it. And because the antennas were stored on the satellite, we actually required a huge power advantage when we perform our uplink. So we require not just big antenna, but a high transmit power to do that. Our lab only has 50-watt transmitter and only antenna that's about 12 dBi gain. So we asked for some help from some of the other radio amateurs. Some of these first attempts did not work, and I believe it's due to the configuration of the radio. There are many possible other aspects that needs to be configured correctly for the uplink to work properly. Unfortunately, I don't think any of these work too well. Finally, we actually had a 25-meter dish in Netherlands that was helping us to transmit a command. So after a lot of discussions and making sure that the setup was correctly done, on 12th of June, a third attempt was made to transmit the packets to Inspire2, and then another attempt to transmit the packets to UNSW ECO. Once that was done, Inspire2 actually started transmitting its beacon. The UNSW ECO did not have its beacon on. And this is when we realized that it could be a TLE problem. So the two-line element orbit propagation model given to us by JSPOC, by NORAD, could be incorrectly tagged. So we might be using someone else's TLE rather than our own TLE. So we checked around, we looked around, and we asked, University of Colorado being one of those people that we asked, came back to us and said, hey, we are using your TLE. So we actually started to think that maybe it has been swapped. So we used their TLE to communicate with our CubeSat instead. And on 19th of June, that happened, that uplink happened, and the first beacon was transmitted right in the next pass over Netherlands on 19th of June. So the beacon has been continuously transmitted and reliably operating since. And since then, JSPOC has swapped TLE labels of Challenger and UNSW ECO. So this slide here shows some of the logs that we have. These are the raw logs, so pardon me for the formatting. It shows the knife activation that correctly deploys the antenna. And following that, we had more issues coming up, so we're not out of the woods yet. Our uplinks have shown to be intermittently failing. So the uplink and downlink is actually operating on a half duplex system. So we have one frequency to operate on, and both uplinks and downlinks have to happen either one at a time. And for that to work properly, we need a correct transmit and receive switching on our LNAs sitting on our ground station. And what we had was an intermittent failure of the switching mechanism. So this switching mechanism here, which sits right underneath the antennas, has an amplifier that's used to amplify the received signal. It needs to switch very quickly, and it also needs to switch many times a day. That has caused that failure being intermittent has made it very difficult to be diagnosed. But finally we did that. We replaced that SSB LNA with a newer version of an LNA that we found, which is the mini kits. It has a much more reliable and smaller packaging of a switching system. So that seems to have worked quite reliably to this day. And following that, we're able to receive some good packets out of our satellites. So we show that there are some good radio signal strength indicator measurements coming out of our CubeSats, and also some very small frequency errors that we can achieve. So occasionally there will be some packet losses, and that is expected. So here are some data coming out of CubeSats. So there's some temperature cycling that we can see here visibly over a period of 90 minutes. So it's thermally cycling as we expect. And our EPS is showing obvious modes where the satellite goes into eclipse, whereby the power, where the current input is quite high and it becomes low once it gets eclipsed, and then going back high again, and we can see the battery level draining as while it's in eclipse. And we also see some magnetometer readings that has been quite stable. We don't see any switching between the magnetic fields, showing that it's actually quite detumbled to a quite well-known state. During the lifetime of operation, we've also been moved around quite a bit. So our ground station actually had to move from one end of the electrical engineering building to the other end, and then from the other end of the electrical engineering building to the computer science engineering building situated here. And even while it was in the computer science engineering building, we had to move our antenna sites being shifted left and right to accommodate some of the roof renovation works. So it has been very challenging for us to operate the satellite. Despite all that, we've managed to still get some good data out of this. We managed to capture this photo as shown by Andrew earlier in March of our CubeSats ADCS camera. So this camera is actually meant for altitude determination. It's not meant for imaging purposes, but we need to do that because our altitude sensors weren't giving us reliable measurements. And from here we can see quite clearly that some burn strings have came into the field of view of the cameras, causing, we suspect that's one of the causes of the altitude sensor to not respond or not work. So our altitude sensors are alive, but it's not giving us any measurements. The takeaway from this is that we've ran a project from using a 200K budget. Since 2012, it's been 6 years in the making. We've made quite significant progress. We've built a lot of infrastructure to support CubeSat developments, and we've trained a number of students that came out of this CubeSat, and it has been a very valuable learning experience for everyone. So I think there is still a lot more that we can do based on what we've learned today. Thank you very much.
Okay, yeah, we're still